Welcome to the notes for Chapter 2, Linear Transformations. We're going to use Sei Chang's notes to do that. The objectives are to interpret simple linear transformations geometrically, to find the matrix of a linear transformation column by column, and to assimilate the two properties that define a linear transformation. This will be seen in a theorem at the end of this section. So as an introduction problem, we can imagine we are coding the coordinates of a point x1, x2 using the following linear transformation. y1 equals x1 plus 3x2 and y2 equals 2x1 plus 5x2. So to decode these coordinates, we need to find a system of equations that yield x1 and x2 in terms of y1 and y2. So we would have x1 equals and x2 equals. So the process takes a few steps, but basically we're going to isolate x1 and substitute it in the second equation until we reach a place where we can have x2 equals 2y1 minus y2. And then in turn we can, from x2, we can find what x1 is equal to by substituting in its equation. So x1 equals y1 minus 3 times what we found for x2. So in the end, x1 equals negative 5y1 plus 3y2. So that allows us to decode the coordinates. If we are given y1 and y2, we can find back what x1 and x2 used to be. Later, we'll see that if we have a matrix 1, 3, 2, 5, then the inverse of the matrix is negative 5, 3, 2, negative 1. So it is the coordinates of the decoding system of equations. A function t is called a linear transformation if there exists a matrix A such that t of x equals A times x for all x in the vector space that we are looking at. So we will just say that t, which is, think of it as a function, it's a linear transformation if there exists a matrix that expresses it. So if every output corresponds to the output of the given matrix or of a matrix, then it's a linear transformation. So linear transformations are functions. The input is a vector and the output is a vector. So instead of maybe the simplest function f of x equals x squared plus 2, where the input is a number and the output is a number, here it's the same idea, but the input is a whole vector and the output is also a vector. Notice that these vectors may not have the same number of components. Maybe x has m components and t of x has n components. All the components, this is a y, all components of y are linear combinations of the components of x. So remember, if we have a linear transformation, it means there exists a matrix such that y equals ax. And if we look at what this means, well, we can see that y1 is a11 times x1 plus a12 times x2 and so on. So y1 is a linear combination of xy, x1, x2, x3, xm, which are the components of x. And likewise, for every row, y2 is a linear combination of x1 through xm, and so on. And a very important note here that we should really be aware of is that in linear algebra, linear, when we talk about something that's linear, it does not include constants. So for example, y equals 2x plus 3 would not be considered linear in linear algebra. We cannot add constants in the end. So a definition, the identity matrix, which we write I2, I4, I sub 2, I sub 4, etc., is simply the n by n matrix that has 1s on the diagonal and 0s everywhere else. So I sub 2 is like this, I sub 4 like that. The value of the identity matrices is that if you multiply any vector or any matrix with them, they stay the same. Let's look at a geometric interpretation of a linear transformation now. If we say that the linear transformation T is defined with matrix A, 0, -1, 1, 0, we would like to see what effect this matrix or this linear transformation has on vectors. So since X in this example needs to be a column vector with 2 components, it means we are going to be in R2. And the output, because A also has 2 columns, is also going to be in R2. So we're going to start with a 2-dimensional vector X, and we're going to end with a 2-dimensional vector T of X. If we look at the effect on vector V, 1, 0, this is what happens, and we get 0, 1. If we look at the effect on vector W, then T of W will be equal to -2, 0. So V, 1, 0, and W, 0, 2, become T of V, which is 0, 1, and T of W, -2, 0. For a general vector X, which is x1, x2, then the output is -x2, x1. And what that is a rotation by 90 degrees clockwise. Whatever vector you have that you input in this linear transformation, the output is that vector rotated 90 degrees clockwise. We will see a lot more about that in the next section. Here we have a theorem whose importance can't be exaggerated, even though it might seem like it's so trivial that it's not important. If you have a linear transformation Tx that's represented by a matrix A, then the ith column of A is T of Ei. So maybe we want to talk about what E sub I is. It's the vector that has a 1 in its ith row. So we have seen a lot of them in multivariable. E1 is 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1, but we used to call these vectors I, j, k. Now in linear algebra we will much more often work in n dimensions, so it's a lot more convenient to call these vectors E1 through En rather than I, j, k, etc., because we don't know where to stop. Now these vectors Ei are going to be called the standard basis vectors. So what this says is that the ith column of matrix A is actually the image of Ei. Let's see how this works. So if the matrix A is written with column vectors v1, v2, v3, then T of Ei is going to be v1, v2, v3 times Ei. And think about it, what is this going to be? If we just look at this horizontally, we get the ith value, the ith vector, will be multiplied by 1, and it'll be the only one that is multiplied by 1. So this is going to end as being equal to Vi. It's worth thinking of matrix A with all its vectors expanded like this, and think of the first row in matrix A is going to be 0 times this, plus 0 times that, plus 0 times that, etc., plus 1 time the value in the ith column, plus 0 times this, 0, 0. And for every row in matrix A, it will always hit the 1 in the same place. It will always hit the 1 in the ith column. So it will gradually build the vector Vi. As a simple example, just to make it more explicit, if we have matrix A here, then T of E2, we multiply A by the vector 0, 1, 0, we can see that it automatically produces the second column, -7, 0, 4. And that's a really important idea. It means that we can basically read the image of all standard basis vectors in the column. So T of E1 is 2, 4, 1, T of E2 is -7, 0, 4, and T of E3 is 5, 3, 6. So we know where all standard basis vectors go. And that's really important because every vector is a combination of these standard basis vectors. So we know the image is actually going to be a combination of the 3 column vectors that we see here. That's something we'll talk about a lot in the future. So finally, the theorem, a transformation T is a linear transformation if and only if T of V plus W equals T of V plus T of W, and T of KV equals K times T of V. So, remember, a transformation is a linear transformation, means that there exists a matrix A such that T of X equals A of X. And we want to show that this fact is equivalent to these two facts together. So, firstly, we're going to go from the top to the bottom. So we're going to assume that T is a linear transformation, which means there is a matrix A that defines the transformation. And we're going to try to show that A and B are automatically true. So if we assume that T is a linear transformation, then there exists a matrix A that defines the transformation. And that means T of V plus W can be written as matrix A times V plus W. And this is equal to A times V plus A times W. And why is that true? We saw it in section 1.3. So refer to section 1.3 to see how this step is valued. And now we work backwards, and matrix A times V is actually T of V, and A times W is actually T of W. So there we go. What about T of KV? We can follow the same process. T of KV is a matrix A times vector KV, and using section 1.3, we know that this is equal to K times A times V, and that is K times T of V. Secondly, we need to go backwards, and we need to assume A and B are both true, and we need to show that T is a linear transformation. So we're going to assume A and B are true, and we're going to show that there exists a matrix A that defines the transformation. We assume A and B are true. We need to show that T is a linear transformation, i.e. there is a matrix A such that T of X equals A of X. So firstly, T of X is equal to T of, if we expand vector X, it's X1 times E1 plus X2 times E2, etc. And by using property A, we can split all these additions, and it's now T of X1 E1 plus T of X2 E2 plus T of X3 E3, and so on. And from here, using property B, we can extract all the factors X1, X2, X3. So we end up with X1 T of E1 plus X2 T of E2 all the way to the end, which can be written, in fact, as a matrix times a vector. It's the matrix T of E1, there's no pluses here, it's just column vectors, T of E1, T of E2, all the way to T of En, times vector X1, X2, Xn. We can see that if I proceed to multiplying, I would get T of E1 times X1, plus T of E2 times X2, plus T of E3 times X3, all the way to the end. And we can say that these vectors, T of E1, T of E2, T of E3, and so on, we can just notice that, hey, that's exactly the matrix I was hoping to exhibit. I wanted to show that there existed a matrix A such that T of x was equal to A times x. And this is the matrix. So this again refers back to what we saw earlier. It's really valuable because if we know the image of the first basis in the first vector in my basis, then I can just put the image of that vector as the first column of my matrix, and I can put the image of the second basis vector as the second column of matrix A. So I can build matrix A very easily just by looking at what happens to E1, what happens to E2, what happens to E3, and each one of these goes in a column. Thank you. See you in 2.2.